Problem 18. So we're going to look at G being a finite group of even order. Even order means that the number of elements in the group is even. We want to show that there must exist an element that's not the identity element, such that the element A, which is the special element we're going to name, equals its own inverse. And then it gives us a hint to use problem 17, which says the inverse of the inverse is itself. So what do we need to know? Here's a quick reminder of what a group is. We have the set and the operation according to these axioms, which we'll be using. And then we also need to know a couple more things. So let's take a look at those. One, if you remember what we did in problem 14, we can cancel on the left or right hand side. So here A star B equals A star C. We have A on the left hand side in both cases, so we cancel out A on the left hand side. Same thing if you have A on the right hand side in both cases, you can cancel out on the right-hand side to just get B equals C. So there's a reminder of what we already did on problem 14. And then here's a new concept possibly for you is the inverse of the element is unique. So for any element, the inverse is unique. We don't know what it is, but there's only one. And here's our proof of that. We won't linger on it too much, but the inverse of any element is unique. So that's what we're going to use. And now let's look at how to solve this problem. So this is a little more in depth than what we've been doing recently, but we're going to set up our group G, and we're going to say G has even amount of elements, okay? And now assume that what we're being asked to prove is wrong. So we're going to assume that for every element that's not the identity, that the inverse does not equal the element itself. And we want to find a contradiction to then show that this is an incorrect assumption. So now that we've assumed that A inverse does not equal A, we're going to look at any element in the group and say, hey, if we have an element, I know we have an inverse. So that means A inverse equals B and B inverse equals A. And that is by problem 17, right? So I could have written A double inverse like it is in problem 17. But another way to write this is just the inverse of A is B, which means the inverse of B is A. That's a property that's always true. We proved it in problem 17. And the idea is that we're pairing up these elements. So if we have an even amount of elements, then each one has its own pair. But we don't want to forget the special case, which is the identity element. Remember, we assumed for all non-identity elements in G. That's because the inverse of the identity element has to be the identity element, right? There exists a special element E such that A star E equals E star A equals A. Well, that means that if E times anything is the other thing, the only way for E to get back to E is to square it, right? If A is non-trivial in the line highlighted here, then it's always not going to equal E. So we know that the identity element itself has its own inverse, which leaves us with n minus 1 elements. But remember, we started with an even amount of elements, so n minus 1 must be odd. And what we showed here in the middle is that we can pair up each of the elements. Call them whatever you want, like A inverse, B inverse, C inverse. Each one's going to get paired up. And because we have an odd number of those, someone's going to get left out, which means that somebody doesn't have an inverse, which is impossible. So therefore, our assumption must be wrong. It cannot be possible that every element does not equal its own inverse under the conditions we imposed, which were G is a finite group with even amount of elements. Thanks for watching this video. I hope you enjoyed it. Make sure to subscribe so you don't miss out on future videos. And if you have a question about this problem or if you'd like to request a solution to a different problem you're working on, let me know in a comment below.